In this video, we will talk about properties of continuous functions. We will start with a review with what it is for a function to be bounded, and also a review of what it is for a function to be compact, as well as the Heine-Borel theorem, which gives us a condition to determine if a set is compact. We'll also review this theorem from continuity and the preimage of open sets. From that review, we will continue with our theorem about compact sets and continuous functions, and then we'll finish with the intermediate value theorem. So first, our review of what it is to be a bounded function. A function is said to be bounded if its range is a bounded subset of R. That is, f is bounded if there exists a real number m such that the absolute value of f of x is less than or equal to m. So this tends to be the condition we use to prove that something is bounded. Unfortunately, a continuous function may not be bounded even when its domain is bounded. And this is our example. So D, our domain, is the interval between 0 and 1, which of course is definitely bounded below by 0 and bounded above by 1. We want to find a continuous function that is not bounded on D. There are many possible answers, but the one that immediately comes to my mind is f of x is equal to 1 over x. If it happens that the domain of a continuous function is both closed and bounded, then the function will be bounded. And in fact, we can prove a stronger result, which is compactness, in the theorem below. But before we do this, I do want to bring back our last example where the domain is the open interval between 0 and 1, which was a continuous, we wanted to find a continuous function on the domain that is not bounded, and our function was f of x is equal to 1 over x. So here it says if the domain of a continuous function is both closed and bounded, then the function will be bounded. And I wanted to comment, for this example, it is not enough then to take D to be the closed interval 0 and to 1, because obviously if you have f of x is equal to 1 over x, it is not bounded. And the reason why it doesn't work for this example is because f of x is not continuous at 0. So in this example of f of x, it doesn't work just to close your interval D in order to satisfy this condition here that the domain of a continuous function is both closed and bounded, because in this case, f of x would not be continuous at x equals 0. And x equals 0 cannot be part of your domain. It would have to be an open interval. Since our next theorem concerns compact domains of a continuous function, I thought we should review what it is to be compact. So f, the script s, if f is a family of open sets whose union contains s, then f is called an open cover of s. So for example, if s is the open interval 0 to 1, which I have drawn here, f1, which is 1/2 to 1/2, and f2, which is 1/2 to 1, and f3, which is 1/4 to 3/4, all contain the union of these three sets is equal to f, and it's an open cover for s because s is contained in the union of f1, f2, and f3. And then, if you recall, s is compact if and only if every open cover of s contains a finite subcover. So in this case, f1, f2, and f3 is a finite subcover. So S would be compact. And then we have this handy theorem, the Heine-Borel theorem, that said a subset of R is compact if and only if it is closed, which means it contains its boundary, and it is bounded. And our last item of review is continuity and the preimage of an open set. So if you have a function from D to R and it's continuous, then every open set G in R, over here in the range, for every open set here, there's an open set in the domain, or the part that intersects the domain that gets mapped and is equal to the open set G. Our first theorem tells us that continuous functions take compact sets into compact sets. So the theorem says if D is a compact subset of R, and suppose f maps from D to R and it's continuous, then f of D is compact. To show that f of D is compact, we have to start with G, an open cover of f of D, and we want to show that G has a finite subcover. And the proof of this theorem is going to fall out when we use this theorem up here that we had reviewed. It was a theorem that related continuity and the pre-image of open sets. And this was the picture that went with it. So from the theorem above, because F is continuous for each open set G of A, and I have a picture of G here, which is open, there's an open set H such that the intersection of H and the domain is a pre-image of G, of A. I decided I needed a different drawing with the real number line instead of the little blob drawings. So this is my domain D, and it is in black. So this here is my domain, and it's along the real number line. Here are my real numbers. And then what I'm saying, or what this theorem starts out with saying, let's let G be an open cover of f of D. So let's say our f of D, our range of our function, let's just say it's actually I'll just do this, from these black parentheses here to here. Okay, so, and G of A is an open cover of f of D. So I have three sets, my blue G1, my green G2, and my yellow G3. Those are three sets, and together they are an open cover. In other words, they totally enclose my f of D. And remember, my f of D here is notated in with the black parentheses. It's an open interval. And then what did I want to say? Then I wanted to say that for each of these open sets in the open cover, G1, G2, and G3, then there's an open set over here in the domain. So H1, actually it doesn't have to be completely in the domain, but the part of H1 that intersects the domain, H1 is an open cover, will then map to G1. And for this, by this theorem here, continuity and pre-image of open sets. So then if I have an open set G2 in green over here, by this theorem, that means there has to be some open set over here that when you intersect it with the domain, H2, will map exactly into G2. Also for this open set G3, that is part of the open cover, there is another open set over here that when you intersect it with the domain, it maps exactly into G3. And I have the what I just said written here in blue for my blue open sets. So G1 is part of my open cover for f of D. And so what I said is there is an open set over here when you intersect it with the domain and you take the function, so f of H1 intersected with the domain is going to exactly equal to G1, or in other words, this H1 intersected with D is the pre-image of G1. And I can write similar statements for H2 and H3. So that's what this here is saying. For each open set GA, there is an open set HA such that the open set HA intersected with the domain is the pre-image of GA. And furthermore, since f of D is a subset of the union of GA because GA is an open cover, and this is what it means to be an open cover, it follows that D then is a subset of the image of GA. In other words, D is completely contained in the image of G1, which is this blue, in the image of G2, which is in green, and the image of G3, which is in H3. And another way, instead of saying the image of G1, we could just say H1, and instead of G2, we could say H2. So in other words, this could just be replaced with the union of HA. Thus, the collection H of A is an open cover for the set D, because D is contained in all the union of the H of A, right here. By this statement here, that's exactly the definition of an open cover. Since D is compact, and how do we know D is compact? It was given to us up here. So D is compact. That means this is an open cover, but D is compact, so there is a finite number of HA that covers D. So in other words, HA1, HA2, up to HAN, it's finite, will cover D. So here D is covered by a finite set of H's. And now, of course, our drawing, I didn't draw an infinite cover, so it's kind of, when you look at this drawing, you're almost fooled into thinking, of course, it's finite. But at this point, we've firmly established that there's a finite open cover for the set D. And now we're going to go and look backwards. So if we intersect each of our H of A's with D, then what we get is this part here is what gets mapped to our G of A's. So in other words, F of D then is covered by this finite number of open sets up to GAN. So in other words, there's a finite number of sets now that will cover F of D. And again, the finite sets came from this finite set that covered D. So we mapped it over and we get a finite cover for F of D. And again, thus our GA1, GA2 up to GN is a finite subcover of G, and F of D now we've proven is also compact. So again, if we have a continuous function, then a compact set will map to a compact set. A corollary, if D is a compact subset of R and F is continuous, then F assumes minimum and maximum values on D. That is, there exist x1 and x2 such that f of x1 is less than or equal to every other f of x, which is less than or equal to f of x2 for all x in D. Let's look at an example. Consider the identity function on the unbounded set 0 to infinity. The identity function is continuous, that is, f of x is equal to x, being the identity function. It is continuous, but it does not assume a maximum value. So why doesn't the corollary seem to apply? And of course, the theorem doesn't apply because this set here, 0 to infinity, this domain, does not satisfy the conditions that the domain is compact. Since D is not bounded, it is therefore not compact by the Heine-Borel theorem here, right? A subset R is compact if and only if it is closed and bounded. So D is not bounded and therefore not compact. So in this case, F may or may not attain its supremum and infimum on D, even if F of D is bounded. Now we have the example, let D go between 0 and 1. Find a continuous function f from D to R such that f is bounded on D, but does not assume min and max values on D. Also here you can see that D is bounded above by 1 and D is bounded below by 0. We can consider the identity function again because f is bounded on D. F of D is bounded. In other words, the maximum value, it's bounded by 1. F of D is bounded by 1. But it does not assume the value of 1 because this is the open interval. So we never actually plug 1 in to the function. So here's an example. F is bounded, but it does not assume its min and max value on D. And again, the reason why we can't use this corollary is D must be compact, and by Heine-Borel, a subset is compact only if it is closed, which D is not, and bounded. And just in case you forgot what it is to be compact, like if you see this open interval between 0 and 1, you can certainly contain it in a single open set, like between, -1 and 2. That would certainly contain it, and that's finite. But to be compact, S is compact if and only if every open cover of S contains a finite subcover. So it's not sufficient to find one finite subcover. What you have to do is find a finite subcover for every open cover. And that's hard to do, to consider every single open cover you can think of, which is why we have the Heine-Borel theorem to give us an easy way of determining if a set is compact. Next, we're going to work our way up to the intermediate value theorem, but first we have a lemma. So if f is a function that goes from a to b to r, and it's continuous, suppose that f of a is less than 0 and f of b is greater than 0. Then there exists a point c in the interval ab such that f of c is equal to 0. So here at f of a we have something less than 0, f of b, we have something greater than 0. And if f is continuous, then at some point, our function must cross 0. So there's some point c such that f of c is equal to 0. I guess this isn't quite drawn correctly because this should be c right here. And our strategy is going to let c be the largest x for which f of x is less than or equal to 0. So more precisely, we're going to look at the set S of all values x in the interval, the closed interval ab, such that f of x is less than or equal to 0. Since we are given that f of a is less than 0, we know a is an S and S is not empty. Also, f of b is greater than 0, so if we're looking at S being all the values of x such that f of x is less than 0, that means f of b, or is greater than, so S is bounded above by b. So C, where is C? C we define to be the largest x for which f of x is less than 0. So C is going to be our sup of S, and it does exist as a real number between a and b. And now our claim is that f of c is equal to 0. So let's suppose f of c is less than 0. So we're going to do this, we're going to prove this claim by contradiction. Then there exists a neighborhood u of c such that f of x is less than 0. So here's our, this is why my drawing was off, because now we're going to assume that that f of c is less than 0. And then here's our neighborhood u of c such that f of x is less than 0. But we also know c does not equal b since f of c is less than 0 and f of b is greater than 0. Thus u contains a point p such that p is between c and b. And we know we can find this p because c and b are real numbers. But we also know that f of p is less than 0 since p is in the neighborhood of u, so p is in S. But this contradicts c being an upper bound for S, which we said here, that c was the sup of S. Thus we have shown that this assumption here, that f of c is less than 0, gives us a contradiction. So that means f of c must be greater than or equal to 0. Similarly, if f of c is greater than 0, then there exists a neighborhood u of c such that f of x is greater than 0 for all x in u intersect ab. Since c does not equal a, then we have f of a is less than 0, which is less than f of c. It really does echo this. Thus, u contains a point p such that p is between a and c. This implies p is an upper bound for S and contradicts c being the least upper bound. So we conclude that this assumption here was false. So if f of c is not greater than 0 and it's not less than 0, then f of c must equal 0. And finally, since f of a is less than 0 and f of b is greater than 0, and f of z is equal to 0, it must be that c is in the interval ab. Now that we have this lemma proved, we can go on to the intermediate value theorem that says suppose f is a function from the closed interval ab to the real numbers and f is continuous. Then f has the intermediate value property on the interval ab. That is, if k is any value between f of a and f of b, that is, k is greater than f of a and k is less than f of b, or the other way around, k is greater than f of b and less than f of a, then there exists some value c in the interval ab such that f of c is equal to k. You've seen this theorem before in calculus, so here's your chance to look at it again and give it a proof. We start with letting k be any number between f of a and f of b. So if f of a is less than f of b, then we're going to apply this lemma here to the continuous function, and so we're going to make a new continuous function g given by f of x is equal to g of x is equal to f of x minus k. Now we're going to plug in a and b into g. So plugging in a into g gives us g of a equals f of a minus k. And since k is greater than f of a, that means f of a minus k is less than 0. Plugging in b, we get f of b minus k, and since f of b is greater than k, we have f of b minus k is greater than 0. So looking at what we have g of a is less than 0, which I've written here, and g of b is greater than 0. So I have this set of inequalities, and by our lemma here, if we apply that, instead of f we have g, then there exists a point C in AB such that g of c is equal to 0. So I have exactly that written here. There exists C in between A and B such that g of c, which if I plug in c into here, that's f of c minus k, is equal to 0, which implies that f of c is equal to k. And looking over here, that's exactly what I wanted to prove. And the idea behind the intermediate value theorem is, let's suppose we have AB here and f of A is somewhere here and maybe f of B, for the sake of argument, without loss of generality, right? We can say f of B is greater than f of A. So intuitively, the graph of f must cross any horizontal line between f of A and f of B. So in other words, since the graph is going to go from f of A to f of B, any horizontal line in between, our graph must cross. So if the graph of f is below y equals k at A, so here's our line y equals k. So it's below, f of A is below our line y equals k, and above at B, so f of B is above y equals k, then for f to be continuous, it must cross y equals k. It must cross this line somewhere in between. Thus, the graph of a continuous function can have no jumps. A more succinct way of saying this is probably if f is continuous and f maps from a to b, then f of x must take on all values between f of a and f of b. Again, there are no jumps. For our first example of the intermediate value theorem, we will show that every positive number has an nth root. We are going to start this proof by using n as a natural number because n is going to be our nth root, and we're going to suppose we have this number k greater than 0, and this k is the one we have in our intermediate value theorem. So again, we've just kind of identified our k, we identified our n, and we're going to start by letting f of x equals x to the nth power. Then next, we're going to note that f of 0 is equal to 0, and that is less than k. And so we're kind of working up to here where we have f, in this case, it's f of 0 is less than k. Now we need something, an f of b, that is greater than k. So we're going to let b equal to k plus 1. And by Bernoulli's inequality, which I didn't remember or know, but here it is, b of n is equal to, since b is equal to k plus 1, it's equal to 1 plus k to the n, which is greater than or equal to 1 plus k times n, which is greater than k. Thus we have b of n, which is f of b, is greater than k. So looking at this, we have f of 0 is less than k, and we have f of b is greater than k, which is exactly the form we want here to use the intermediate value theorem. And since f is continuous, we can use the intermediate value theorem. There exists a c such that c is between 0 and b, and f of c is equal to k. That is, f of c is equal to c to the n is equal to k. Thus, c is the nth root of k. So that's pretty clever. So again, to find the positive nth root, we let f of x is equal to x to the n. We noted that f of 0 is equal to 0, which is less than k, and k is just some number greater than 0. Then if we let b equal k plus 1, we use the Bernoulli inequality to show that b to the n, which is 1 plus k to the n, is greater than k. That's f of b, because this is f of b is greater than k. So we have these two things here, that we have f of 0 is less than k, which is less than f of b. So by the intermediate value theorem, we must have a c between 0 and b such that f of c is equal to k. which is f of c is just c to the n is equal to k, so c is the nth root. So the intermediate value theorem is a very powerful result that can be used in a variety of settings. Here is an example that you can kind of read through. I'm not going to go through it because it's really kind of beyond what we have learned so far, but there's kind of an outline of a proof here if you'd like to read it. I will give you this example. Assuming cosine x is a continuous function, prove that x equals cosine x for some x in the interval 0 to pi over 2. To do this proof, I'm going to introduce a new function f of x, which is going to be equal to x minus cosine of x, which is just x minus this side of the equation. And the reason I'm doing that, if I can show that f of x is equal to 0 for some value, then I'm going to have 0 is equal to x minus cosine of x, which is the same thing as saying there is some value x, which is equal to cosine of x. And I can show that f of x equals 0 if I can find an a and b such that f of a is less than 0, which is less than f of b. And then I could use this lemma to show there's a c and a such that f of c is equal to 0. So that's my game plan. And again, I'm going to start with f of x is equal to x minus cosine x. And now I need to find an a and a b such that a is less than 0 and b is greater than 0. So f of 0 is equal to 0 minus cosine of 0 is 1, so it's equal to negative 1. So this is my a, my f of a that's less than 0. And then if I plug in pi over 2, I get pi over 2 minus cosine of pi over 2, which is 0, so I get pi over 2. So this is my value b, which is greater than 0. And since f is continuous by this lemma here, there's going to exist an x naught inside my interval 0 to 2 pi such that f of x naught is equal to 0. And that is x naught will be equal to cosine of x naught. And I have proven what I wanted to show. So now we've covered the main topics of this video. We reviewed what it is to be a bounded function. We reviewed the definition of a compact set and also the Heine-Borel theorem, which gave us a way of easily determining if a set is compact. We talked about how a continuous function will map, will have, for any open set in a continuous function, the pre-image will also be an open set. And then we talked about for a continuous function, it'll map compact sets into compact sets. We also said if D is a compact set and we have a continuous function, then F will assume its minimum and maximum values on D. And then we talked about the intermediate value theorem. First, we went through the lemma. If F is continuous and we have some value less than 0 and some value greater than 0, then there must exist a point C such that that point C, f of C, is equal to 0. And we did the intermediate value theorem. And then there's another theorem I should also mention. Let I be a compact interval, and suppose that f goes from I to R and it's a continuous function, then the set f of I is also a compact interval. Now that we've gone over the material, there are two problems, one of them with multiple parts, for you to try by way of review. So pause the video, give the problems a try, and on the next slide I'll have solutions. Here are the solutions. And that's it for this video. Thank you for watching.